Log on, tune in, find out. Another good idea from Cambridge.
And it's a real pleasure to have George Ellis with us tonight. He's now Professor Emeritus, which means he's served enough years to do what he wants and not to sit on things he doesn't want to do, from the University of Cape Town in South Africa. And his research work really has been on a variety of things: relativity theory, cosmology, complexity studies and the brain, that sort of thing. But he's also very interested in the science-religion debate, which is why we've invited him here tonight. He's written a number of papers on that. He's taken part in Vatican Observatory workshops, written a book with Nancy Murphy on the moral nature of the universe, and a variety of things. He's also been a past president of the Royal Society of South Africa, and I'm really pleased to say that as of this summer he's joined the Royal Society, been elected as a fellow of the Royal Society in London. So this is a good occasion for him to come and speak to a British audience. So I think without further ado, I'll pass over to George Ellis. We'll plan to talk, he'll talk for 50 minutes or so, and then there'll be a chance for questions at the end, so do store them up. And then afterwards there will be refreshments and a bookstall at the back. The only one thing I might say is, so as not to embarrass yourself, it would be a good idea to switch off your mobile phones at this point. Thank you very much, George.
Well, thank you for the invitation to come and speak here. I'm very pleased to be here again. I had many interesting years in Cambridge. Ultimate causation, and the organisers particularly asked me to add in the words "and God." So I will be talking about that. But I do think if one wants to talk in the science and religion area, one must be very clear to get the science right. So quite a lot of this talk is about the science of multiverses and cosmology. Well, the idea of a multiverse, or an ensemble of universes or of universe domains, has received increasing attention in cosmology in recent times. People think of this multiverse or these multiverse domains as separate places in one great big universe, so a huge universe with what people call multi-universe domains or multi-universes, each with different properties in a spatially separated way. What could happen in separate times? The universe goes through oscillations and it repeats the same kind of thing many, many times. You could think of it taking place in times. The quantum theory leads some people to believe in a quantum branching multi-universe where there are many other branches of the quantum wave function of the universe. And that's something I'm not going to talk about. It's something I don't really understand, and I don't myself really see what it gains one. But one of the most prominent ways it's been talked about in recent times is string theory, the current theory of unification of gravity and general relativity, has led to something called the cosmic landscape embedded in a chaotic cosmology, and I will talk a little bit about that further shortly. And Leonard Susskind's book on this, which I will mention, is the prime example there. And then there are other people, including my old supervisor Dennis Yama and Max Tegmark, and I think to some extent Martin Rees, who talk about totally disjoint universes, that there are billions and billions out there of totally disjoint universes that aren't even connected to us in any way causally. So the idea of the multiverse has been put forward in many different ways. Possibly the most prominent at the moment is that one of the cosmic landscape embedded in a chaotic, inflationary cosmology, but there are these other ways of trying to talk about it. Now, the big issue that I want to raise right at the beginning, in my view, the very nature of the scientific enterprise is at stake in the multiverse debate, because the multiverse proponents are proposing, in my view, weakening the nature of scientific proof in order to claim that multiverses provide a scientific explanation. And in my view, this is a dangerous tactic. And I want to emphasize we're concerned in the multiverse story with really existing multiverses. There's no problem with potential multiverses or hypothetical multiverses. You can think, if you like, in your mind of ensembles. There's no problem with that. The problem comes when people claim up there really are millions and millions, and often people use the words an infinite number of other universes or other universe domains like the one we can see. The point is, we want to discuss whether they actually really exist. Two central scientific virtues are testability and explanatory power, and in the cosmological context these are often in conflict with each other. You can often have a theory which is great on testability but not very good for explanatory power, or you can have ones which are very good on explanatory power and not testable, and there's a balance between these which one wants in cosmology. Now, the extreme case here is the multiverse proposals, where no direct observational tests of the hypothesis are possible, as I would explain in detail. As the supposed other universes cannot be seen by any observations whatever, underlying physics is also untested and indeed probably untestable. In this context, one must reevaluate what the core of science is. Can one maintain one has a genuine scientific theory when both direct and indirect tests of the theory are actually impossible? Many of my colleagues are claiming this is a scientific theory. They include Martin Rees, the president of the Royal Society. And he is strongly saying multiverse idea is a scientific proposal. And as we'll see, I claim it is not a scientific proposal, it is a philosophical proposal. And that's the thing that I'm going to pursue. If one claims that multiverse is a scientific one, in my view, one is altering what one means by science. And I think one should be very, very careful before so doing. Now, the motivation for the multiverse, there are various ones. One, it's claimed as the inevitable outcome of the physical originating process that generated our own universe. And for instance, in particular, what's called the chaotic inflationary scenario. Secondly, it's seen as the result, perhaps by some other people, of a philosophical stance underlying physics, the idea that everything that can happen, happens. And some people think that's a fundamental idea underlying scientific the way science works, because it's a logical conclusion of the finite path integral approach to quantum theory. But many people are pushing it because it's an explanation of why our universe appears to be fine-tuned for life and consciousness. And that's the one which I just want to pursue for a short while, the anthropic issue. According to Barrow and Tipler, the universe is fine-tuned for life. This is both as regards the laws of physics, as Max Tegmark, for instance, makes it claim, and the boundary conditions of the universe. You've got to get the laws of physics right, and you've got to get the boundary conditions of the universe right if life is going to exist. And the idea here is a multiverse with varied local physical properties is one possible scientific explanation. So you imagine an infinite set of universe domains in which all possibilities occur, and some are very bad for life, most are very bad for life, but here and there, in this multiverse where all sorts of physical possibilities occur, just here and there things turn right out for life, and therefore life will flourish in the multiverse, because so many options happen that somewhere it's bound to get it right. Somewhere things will work out, things will be okay for life, and that's the way many people try to explain the existence of life, because somewhere in the multiverse things will work out right. Now, I emphasize again, this must be an actually existing multiverse if this argument is going to work. It's no use saying I've got a hypothetical multiverse in which somewhere, you've got to say there's an actually existing one where somewhere things work out right. And this fine-tuning, a lot has been written about it. I'm just going to quote from Martin Rees's book, Just Six Numbers. One of the things that has to be right for life to exist is the ratio of the electric force to the gravitational force, this huge ratio of 10 to the power 36. You've got to get that right very, very close to your life won't exist. The strength of the nuclear binding force must be just about right in terms of that dimensionless number. If you get it wrong, you won't get nuclei, or you will get everything will form into diprotons. You've got to get the thing right, or else no complex atoms of any kind will exist, allowing life to come into being. The normalized amount of matter in the universe, which is 0.3 in terms of a dimensionless parameter, that must be right, because if there's too much, everything will collapse into black holes. If there's too little, you won't get clusters of galaxies forming. The cosmological constant, which is this force which is making the universe accelerate at the present time, has been measured to be about 0.7. It must be within an order of magnitude of 0.7 again, otherwise galaxies won't exist, because if it's too large, galaxies will get blown apart before they can form. If it's too large and negative, then everything will just collapse. You've got to have seeds for cosmic structures, 1 part in 10 to the 5th. And you've got to have, many people have thought, in order for life to come into being, 3 spatial dimensions. And these have all been discussed in detail. I'm not going to go into them in detail here, except to say there are many, many aspects of physics and aspects of the universe. The electric to gravitational force is physics, the nuclear binding force is physics. The amount of matter in the universe is a cosmology thing. The normalized cosmological constant is something which comes from physics. The seeds for cosmic structure comes from cosmology. You've got to get them all right, we believe, in order that life comes into existence. And so if you imagine a creator creating billions of universes or a random process creating billions of universes, and most of them, some of these numbers may be right, but they won't all have the right value. And the particular application is in terms of the small value of the cosmological constants, famously explained by Steven Weinberg, and then Susskind pursues this in his book, The Cosmic Landscape. Fundamental theory says the cosmological constant should be huge, of the order 10 to the 120. The value which we measured is about 0.7. There's a vast discrepancy between what simple fundamental physics says for this and what we actually measure. And we have no theoretical explanation for why it is from the standpoint of fundamental physics. Anthropic considerations must mean the value of lambda will be very small, because if it is too large, as I've already said, galaxies won't form, they will get blown apart by this repulsive force. You've got to get it within an order of magnitude of 1, or else there won't be any galaxies at all. So you've got to justify an actual value extremely different from the natural one predicted by physics. In fact, there's a difference of 120 orders of magnitude, and this is a classic example where the multiverse has been used as an explanatory device. You assume in this multiverse that all possible values of lambdas occur, and most of those values will, because of these theoretical arguments, be wildly wrong. There won't be the slightest trace of structure in those universes because they'll be incredibly smooth, but some of them will be out in the wings, and out there will be some universes with small lambdas that will allow life to exist. And this is in fact the multiverse project. It's making the extremely improbable appear probable. That's what the true multiverse project is. Now, I want to explain the key observational point. And the key observational point is that the domains considered are beyond the particle horizon and therefore unobservable. This is a diagram of our past light cone. Is there a pointer of some kind? No, okay. I can show you here. This is our time-like world line. That's time going up, space going sideways. This is the beginning of the universe down here. That's 14 billion years from the start of the universe to the present day, where we are here and now. Oops. And light has been coming to us on our past light cone, this path in space-time. And as you go back into the past, from the present day, the light cone gets collapsed in because the gravitational force of the universe is so large. Going forwards in time, the light which we received today spread out and then came back in, and that's the path in real spatial distance of our past light cone. It's a bit difficult to see what's happening in this diagram, so what cosmologists do, sorry, by the way, what I should explain here is that this is the world line of our galaxy, that's the world line of another galaxy, that's another one. These lines spreading out here are the expanding universe, the expanding galaxies that we see, and this galaxy, for instance, was born there, it crosses our past light cone there, it sends off light which we receive, so we see that galaxy at that instant, we see this galaxy at this instant. Now, this diagram is a bit difficult to handle because everything gets crunched up at the bottom. So what cosmologists do is they expand it, following the work of Roger Penrose. What we've done here is we've expanded the spatial dimension so that all the galaxies now are at the same distance. All galaxies here move on vertical lines in this diagram. What that means is this doesn't represent spatial distance properly. In fact, it represents spatial distance very badly. But what it does do, it represents causal relations beautifully. Because we've done it so that the light cone is at 45 degrees, and that means it shows us very, very clearly how causes work. And the light by which we see the universe comes up this light cone at 45 degrees and up that one. And so this galaxy now, in this diagram, it's the same universe as before, but in a different representation. It's created down here, and it comes up, it emits the light here, and we see it up here. So this is a space-time diagram which shows the causal structure correctly. It distorts the spatial distances, but we've sacrificed spatial distance because we want to see how causation works. And what you can see very clearly is from this space-time point here, we can see down to there, we can see down to there, we can see every galaxy whose world line lies between there, but we can't see any galaxies which lie outside. And this one here is the horizon, that is the limiting galaxy which we can possibly see, the limiting matter that we can possibly see. So this is a diagram showing the limits of what we can see in the universe. Now, that is the one patch we can see about 10 to the 14 billion, about 10 to the 14 light years across. What we can see is inside there, and that's the start of the universe, and we can't see anything outside. Now, to relate this to the multiverse, you must put it in a clearer way. In terms of the multiverse, this is looking at a much bigger patch. This is the entire visible universe that we can see, and this is a further part of the universe beyond the horizon. Now, there's no reason to think that galaxies stop at the horizon, because there's nothing special about what we see at the horizon. So, in fact, it's very sensible to think that what happens outside here is very similar to what happens inside here, but of course that's an extrapolation. There's no observation on whatever data, whatever available for what's happening out there, because all that we can see is this little patch here. So this is a causal diagram of the universe showing the bit we can see, and then the hypothetical bits out there which we can't see. On a better scale, this shows how it works. Because you see, the multiverse claim is that there's this expanding universe patch there, there's another one there, there's another one there, but they use the phrase infinite. What that means is, on the scale you're seeing here, the bit we can see is that little bit, but from what you can see in that patch, people are extrapolating to what is going on in Cape Town, and what is going on at the moon, and way, way beyond. On the scale of this one, there is an incredible extrapolation taking place. From this tiny little patch here, when we put it on this scale, that's the entire visible universe, 14 billion light years. We are extrapolating not just to here, not just to here, but for hundreds and hundreds of times more, 10 to the 500 times more. In fact, people use the phrase an infinite time more. The assumption is we can extrapolate to 100 Hubble radii, 10 to the 1,000 Hubble radii, much, much more to infinity. Go to Cape Town on this scale, and you haven't even begun the extrapolation that is involved in the multiverse extrapolation, where people say the multiverse goes on to infinity. Okay? So there's an extraordinary extrapolation observation. What I'm trying to make clear to you is the multiverse idea is not even remotely observationally testable. Given the situation, what are the arguments and evidences for the existence of the multiverse? First is what Martin Rees calls a slippery slope. There are plausibly galaxies just beyond the horizon. I was just making that point, where we can't see them. So plausibly many different expanding universe domains where we can't see them. And basically the idea is, because you can say they exist just a little bit beyond, you can keep on saying they keep on existing further and further and further and further away. You're just extrapolating a little bit a step at a time. And of course, you're assuming things continue continuously when you do that. This is an untestable extrapolation. It assumes continuity that may or may not be true. Outside where we can see there might be a Robertson-Walker model, the same kind of universe model. In the old days when I started cosmology, we all assumed the same universe continued exactly unchanged for infinity. That was the assumption that was standing when I started cosmology. There might be a chaotic inflation model where you would go out there and suddenly there's a wall, and then there's a completely different kind of universe, and there's another wall, and there's a completely different kind of universe. That would be chaotic inflation. There might be a closed model that closed up on itself on a very, very large scale. We might be living in an island universe. Maybe there's this expanding patch in which we live, and when you go far enough away, maybe space becomes asymptotically flat. These are all possibilities. No test can be done to see which is the case, no observational test. If each step in a chain of evidence is well understood and tenable, then indirect evidence carries nearly as much weight as direct evidence, but not all the steps in this chain are tenable. If employed, this leads to the old idea of spatial homogeneity, forever the cosmological principle, rather than the multiverse of chaotic cosmology with domain rules separating the phases. So that's one argument, the slippery slope you extrapolate. Well, extrapolation is dangerous. Second idea is that it's implied by known physics which leads to chaotic inflation. The key physics is something called Coleman-DeLucia tunneling. It's extrapolated from known and tested physics to new contexts. And the idea is that in our universe, a bubble takes place and an exponentially expanding universe starts off. That then collapses into a new expanding phase like our one. Within that one, another bubble starts off expanding exponentially. And this thing just keeps going on until you have a huge bubbly type of universe out there with exponentially expanding domains, and domains like the one we see at present, but with different values of the constants, and that's chaotic inflation. It's based on physical idea of Coleman-DeLucia tunneling. Now that's an extrapolation from known and tested physics to new context, and the extrapolation is unverified, and indeed I suggest is unverifiable. It may or may not be true. The physics is hypothetical rather than tested. What we are told, or what people would like us to believe, is that known physics leads to the multiverse. The true situation is known physics is extrapolated to hypothetical physics, which leads to the multiverse. And that, in my view, is the correct situation. the multiverse is not the result of known physics, but it is the result of a major extrapolation of known physics to an untested domain, and it is that untested extrapolation which leads to the multiverse you will find presented in many of the books I will refer to shortly. This is a great extrapolation from ionic physics, and this extrapolation, I think, is untestable and may or may not be correct. The third idea is it's implied by inflation, this inflationary idea justified by the cosmic background radiation observations, the famous observations we've been making of the micro-background sky, the Kobe map most of you will have seen in some cosmology talk about. This is the fluctuations in the micro-background radiation on the surface of large scattering. I'm not going to talk about that now, except to say these observations are wonderful observations. They are implied by some forms of inflation. They're implied by inflation. Now, does the fact that we see these fluctuations in the sky imply that chaotic universes, chaotic inflation exists? And I would suggest no. Chaotic inflation is implied by some forms of inflation, by not others. Inflation is not yet, in fact, a well-defined theory. We don't know what is supposed to make this enormous expansion of the very early universe, but the key point is not all forms of inflation lead to chaotic inflation, and as a particular example, you can have a very, very small closed universe, one in which we see right around the universe. And you can have that very small universe inflating, and that will satisfy all the dynamical conditions of standard inflation, but it doesn't have the infinities, which are the core thing which chaotic inflation relies on. Now, another argument is that this is implied by probability arguments, and the idea that particularly Weinberg and Rees have been pushing is the universe is no more special than needs be to create life. The universe is no more special than needs be. If the universe was too special, that would be suspicious. But if it's special enough but not too special, that's good, is the basic idea. And hence the observed value of the cosmological constants claimed in confirmation. And this was developed in a lot of detail by Stephen Weinberg and Martin Rees, for instance. Now, my first comment is, this is a probability argument. The universe is no more special than it needs to be in probability terms. But the key point about this, the people who make this argument assume that they can use a probability argument. Well, you can only use a probability argument, a statistical argument, if a multiverse exists. If there's only one universe, a probability argument simply does not apply. So they're applying an idea which assumes already the existence of the multiverse and simply doesn't apply. It has no validity if there is in fact only one single universe. If there's only one object that we can observe, one object that exists, we can do many observations of that one object. It's still only one object, one universe. And you can't do statistical tests on one object if it is the only existent entity, if there's nothing else to compare it with. Furthermore, we don't know the measure to use, but the results depend critically on that measure. In fact, from my viewpoint, this whole argument is not a proof of multiverses in any sense. It's a weak consistency test on multiverses, indicative but not conclusive. Because a probability argument, in fact, can never be falsified. You can say something is improbable, fine, so it's improbable. That's the conclusion. That doesn't prove it cannot exist. In fact, if you do a probability argument, that already says it is possible it exists, because you can't do the probability argument unless the possibility is already there. Consistency tests must be satisfied, but they're not confirmation unless no other explanation is possible. This is, in my view, a weak consistency test, but it cannot be applied to prove a multiverse exists, because if there's only one universe, this argument doesn't begin to apply. Now, what has been emphasized by Susskind, the idea can be disproved if we determine there are closed spatial sections in the universe. If we were to find the spatial curvature of the universe is positive, this would imply that spatial sections close up, and Suskind's version of the multiverse demands that the spatial sections of the universe are infinite. So the claim is that only negatively curved Robertson-Walker models can emerge in a chaotic inflationary multiverse. This is from Suskind's book. There are two reasons for this. Firstly, because Coleman-DeLucia tunneling only gives k is -1. Well, that claim is already disputed. There are already papers suggesting k is +1 tunneling is possible. Indeed, this depends, as I've already said, on a very speculative, specific speculative mechanism which hasn't been verified to actually work, and such verification is probably impossible. But then there's another point. If the spatial sections are necessarily closed, and all that there is, if the space sections are necessarily closed, which is what happened in K's plus 1, if you continue K's plus 1 models closed curvature ones far enough, they close up on themselves, and then the universe isn't infinite with all these other parts because this closed thing is all there is. But we could live in a high density lump, as far as we can see, and it could change from high density to low density beyond the horizon. And the extrapolation may not be valid. These are somewhat technical points. Neither is inclusive. There is one case, however, in which chaotic inflation version of the multiverse can definitely be disproved, and that is if we observe a small universe. If we could prove, we have already seen around the universe many times. In that case, we would have proved it is indeed spatially closed, and we would have disproved the multiverse of chaotic inflation. And there are various ways to do this. It's possible that the universe is so small that we see the same galaxy in different directions in the sky many times over, and that actually, to me, in my mind, is a very fascinating possibility. That's very difficult to detect, because you would see those galaxies at different times in their histories from different directions with different absorptions, so it's actually very difficult to tell if you're seeing the same galaxy in different directions in the time. But what you can do is search in the cosmic background radiation for identical circles. And it's an exact theorem that in all these situations of a small universe, there must be in the cosmic background radiation sky circles in the sky in which the fluctuations are exactly identical. And that's a test that can be done and is being done. It's a very important test, as if it was ever to work out, it would disprove the chaotic inflation variety of the multiverse. However, not seeing them would not prove a multiverse exists. Their non-existence is a necessary but not sufficient condition for multiverse existence. These tests are being done. They're working out a bit negative at the moment. At the moment, it looks like the universe is not closed on these small scales, but that's not proven fully. Okay, the science part is almost over. I just want to go through the other explanations. One explanation people will give you is that the multiverse is the only physical explanation for fine-tuning the parameters that lead to our existence, in particular the value of our cosmological constant. I've been through that, so that's one argument. But the question is, does that argument prove a multiverse exists? Okay? It's a theoretical explanation, it's not an observation. It's a good theoretical explanation, but the question is, if someone comes to you and says, I know multiverse exists because it's the only explanation we've got for the small value of the cosmological constant, has he given you a proof? No. He's given you a theoretical reason for believing in the multiverse, but he hasn't given you an observational test of whether the multiverse exists. Similarly, according to Sharma, Lewis, Deutsch and others, in effect, a multiverse results from the theory that everything that can happen happens. Okay? And if you believe that's the most fundamental principle of physics, maybe on some quantum mechanical grounds, then it will follow that a multiverse exists, perhaps because everything that can happen happens. Again, it's a theoretical explanation, not an observation. How would you prove it is true that everything that can happen happens? Well, you can't. So again, what you're doing here, in both of these cases, you've got to decide what's more important in cosmology: theory, explanation, or observation, tests against reality. And what is happening in these two cases is people are proposing to us we should place theory above observation. And that is the dangerous trend in science, which we are seeing in the multiverse, is people telling us, don't worry about the observations, worry about my theory. The final point in the scientific part of this talk is the often claimed existence of physically existing infinities, of universes, spatial sections in the universe, in the multiverse context, is dubious. Vilenkin's recent book, Many Worlds in One, The Search for Other Universes, makes this claim very explicitly. Not just that there's a very large number of other universes out there, but there's an infinite number, and he emphasized the infinite. I think that's dangerous. In fact, I think that's completely wrong. Infinity is not a big number, it's an unattainable state. And people treat infinity as if it was just a big number, but it isn't. The very concept of infinity, it's something which cannot be attained. David Hilbert said, the infinite is nowhere to be found in reality, no matter what experiences, observations, and knowledge are appealed to. So, on theoretical grounds, Hilbert, one of the greatest mathematicians ever, believes it's a mathematical idea, but not something that actually exists in reality. And the point about this is one must realize, and we're so used to using the word infinity, we think of it just as a big number, but it's nothing of the sort. Infinity is far, far more than any number that you can ever imagine. It is exactly the statement, it's a number that cannot ever be attained. It's not a number that can be attained. And that's David Hilbert's point. Furthermore, supposing it was correct that the universe was infinite, that is completely untestable. Supposing there was actually an infinite number of galaxies in the universe. Now, firstly, we can't see them, but let's suppose for the moment we could see them. You couldn't prove there was an infinite number without counting them, and that would take you an infinite amount of time, because there's an infinite number of galaxies. You would never finish counting them before the end of the universe. The idea of infinity is completely unprovable in any observational sense. So in my view, the often claimed existence of physically existing infinities is not a scientific statement if science involves testability by either observation or experiment. The claim in the multiverse context emphasizes how tenuously scientific the multiverse idea is. It's a huge act of hubris to extrapolate from one small domain to infinity. Remember that little domain of what we could see? The people who say that there's an infinite number are extrapolating not just 10 to the 1,000 Hubble radii away. You haven't even started to infinity once you reach 10 to the 1,000 Hubble radii away. They're saying you can continue extrapolating forever and nothing ever changes. We got it right from this tiny little patch about what's happening over there. I used to have an analog for this many years ago, in which I would talk about an ant in the Sahara climbing a sand dune, and the ant looks around the Sahara and he says, "Why, heavens, the entire world is made of sand dunes." Okay, well, the ant doesn't get it right because of the horizons. This idea of the often claimed existence of physically existing infinities is not remotely testable. It's a theoretical idea which cannot be tested. Okay, the implications. The multiverse idea is not provable either by observation or as an implication of well-established physics. It may be true, but cannot be shown to be true by observation or experiment. It does have great explanatory power. It does provide an empirically based rationalization for fine-tuning developing from known physical principles. John must distinguish between explanation and prediction. Successful scientific theories make predictions which can be tested. The multiverse theory can't make any predictions because it can explain anything at all. On the basic multiverse idea, everything possible is occurring out there. So it can explain anything. You think of anything you like, and somewhere in the multiverse it's happening. What that means is the multiverse idea can't make a prediction which can be falsified because it predicts everything possible happens. Any theory that is so flexible isn't testable because almost any observation, whatever, can be accommodated. There are some exceptions. I've talked about the closed spatial sections. Apart from that, any other observation can be accommodated. The book's pushing this. Martin Rees, Our Cosmic Habitat, explores the notion our universe is part of a vast multiverse, an ensemble of universes in which most of the other universes are lifeless. What we call the laws of nature would then be no more than local bylaws imposed in the aftermath of our own Big Bang. In this scenario, our cosmic habitat would be a special, possibly unique universe where the prevailing laws of physics allowed life to emerge. Max Tegmark, parallel universes, not just a stable of science fiction, other universes are a direct implication of cosmological observations. That's a scientifically irresponsible statement, in my view. Then it's Susskind. The questions such as why is a certain constant nature one number rather than another may well be answered by somewhere in the megaverse. The constant equals this number. Somewhere else it is that number. We live in one tiny pocket where the value of the constant is consistent with our kind of life. That's it. That's all. There is no other answer to the question. The anthropic principle is thus respectable, and intelligent design is just an illusion. In this book, Susskind confuses the particle and event horizons in order to try to say this is a testable idea and ignores the best data on curvature. It's a very unreliable book. Many worlds in one, the search for other universes, Alex Vilenkin. He goes on to posit our universe is but one of an infinite series, that word infinite. Many of them populated by our clones. Vilenkin is well aware of the implication of this assertion. Countless identical civilizations to ours are scattered in the infinite expanse of the cosmos. With humankind reduced to absolute cosmic insignificance, our descent from the center of the world is now complete. This is presented as an established scientific fact when it's nothing of the sort. By contrast, are universes thicker than blackberries by Martin Gardner? One of the most astonishing recent trends in science is that many top physicists and cosmologists now defend the wild notion that not only are universes as common as blackberries, but even more common. Gardner goes straight to the point. The scientists who say this give no evidence for believing that the possible worlds other than this, useful though they may be as fictions, have real existence. Bernard Kahn, recent developments in cosmology and particle physics, such as the string landscape picture, have led to the remarkable realization that our universe, rather than being unique, could be just one of many universes. Since the physical constants are going to be different in other universes, the fine-tunings which appear necessary for the emergence of life may also be explained. Nevertheless, many physicists remain uncomfortable with the multiverse proposal since it's highly speculative and perhaps untestable. If you want a balanced book, which looks at both sides of the arguments, this is the book. I conclude that multi-universe proposals are good empirically based philosophical proposals for the nature of what exists, but are not strictly within the domain of science because they're not testable. I emphasize there's nothing wrong with empirically based philosophical explanation. Indeed, it's of great value, provided it's labelled for what it is. It's empirically based philosophical explanation. That's what it is. I suggest cosmologists will be very careful not to make methodological proposals that erode the essential nature of science and the enthusiasm to support specific theories as being scientific. For if they do so, there will very likely be unintended consequences in other areas where the boundaries of science are in dispute. It's dangerous to weaken the grounds of scientific proof in order to include multiverses under the mantle of tested science. For there are many other theories standing in the wings who would like to make that claim, to claim that mantle. It's a retrograde step towards the claim that we can establish the nature of the universe by pure thought and don't then have to confirm our theories by observational experimental tests. It abandons the key principle that has led to the extraordinary success of science, namely you must test by observations. In fact, we can't establish definitively either the existence or the nature of expanding universe domains that are out of sight and indeed out of cause of contact with us. The claim that exists is a belief rather than established scientific fact. It's a reasonable faith with strong explanatory nature, but it's a belief nonetheless. The appropriate statement we can make is not multiverses exist, or multiverses have been proved to exist, or even multiverses can be proved to exist, but rather that multiverses exist is a useful hypothesis. That multiverses exist is a useful hypothesis. We shouldn't state more. Now, I want to turn finally to the philosophical kind of implications. Is there a philosophically preferred version? I'm not going to go into this one, but there's an idea from Smoller that a kind of cosmic Darwinism could apply to multiverses. I'm going to leave that one because I want to talk about some more other ones more interesting to this audience. Does the idea of a multiverse preclude the monotheistic idea of a creator God? Is the idea, in fact, contrary to the idea of a creator as it is explained explicitly by Susskind? No, the answer is no. Already foreshadowed by Olaf Stapledon in his book Star Maker, the ideas of God and the multiverse can exist together. God could have chosen to operate via creation of multiverses instead of a single universe. The multiverse proposal says nothing about ultimate causation. Is the ultimate reason for the multiverse chance or probability or inevitability or design? The multiverse proposal doesn't touch ultimate causation because it can't. All the same anthropic principles arise for a single universe, arise from the multiverse. Why this multiverse, not another one? Why a multiverse that allows life to exist? I can make you many multiverses in which none of the universes allow life to exist. So the multiverse proposal, both it is consistent with the creator God if you have that viewpoint of the world, because God could have created many universes instead of one, why not? And on the other hand, the same anthropic principles arise from a multiverse. Why a multiverse which allows life to exist? It doesn't solve the ultimate issues at all. And I want to emphasize something now. All of the arguments produced by all of those books are purely physical arguments, and that's something which I would challenge. Purely physical arguments encompass only a part of the data available to us. Physics only encompasses part of the causal nexus in the real universe. For instance, there is indeed meaning in the universe, no matter what some eminent physicists may say. Meaning is not a physics concept. Meaning undoubtedly exists. If meaning didn't exist, you wouldn't be here. You are here because you think it's meaningful to have a discussion about these issues. Meaning exists in the real physical universe. There is, for example, also good reason to believe in a moral reality, absolute standards of good and evil, nothing to do with physics. What's interesting about here, Dawkins and Stenger both believe in an absolute moral stand, because both of them claim religion is evil. On what standards do they decide that religion is evil? It's because they implicitly, whether they tell you or not, both Dawkins and Stenger believe in a moral reality, otherwise they couldn't make this claim that religion is evil. So the point I'm making now, all of that multiverse argument is based only on physics. Physics is not the only causal thing happening in the universe. How does morality arise? How does meaning arise? Can it come from nothing, or does it reflect an undersigned aspect of the nature of the universe? Because definitely meaning exists, definitely morality exists, even according to Stenger and Dawkins. One can claim that the latter makes sense, that the fact that meaning exists in the lives that we experience is a reflection of the underlying nature of reality and could not come into existence unless the underlying reality in some sense or other embodied both meaning and morality. One can claim that makes more sense and applies either to a universe or a multiverse. It's a quality of existence that reflects what truly exists. I want to just try to illustrate this with a couple of quotes. I like to walk alone on country paths, rice plants and wild grasses on both sides, putting each foot down on the earth in mindfulness, knowing that I will walk on the wondrous earth. In such moments, existence is a miraculous and mysterious reality. People usually consider walking on water or in thin air a miracle, but I think the real miracle is not to walk on water or in thin air, but on earth. Every day we are engaged in a miracle we don't even recognize. The blue sky, white clouds, green leaves, the black curious eyes of a child, our own two eyes, all is miracle. That's trying to alert us to the miracle of existence. That doesn't just apply to us, it applies to the universe or to a multiverse. Why does either of those exist? That is a mysterious factor which cannot be explained by scientific terms. I say to myself as I watch the niece, who is very beautiful, in her this red is transmuted into melancholy grace, into modesty, into a gentleness without words. Sensing my gaze, she raised her eyes towards mine and seemed to smile, a mere breath on the delicate face of the waters, but an affecting vision. I sense the mysterious presence of the soul that is unique to this place. It fills me with peace, and I mind with the words, this is the peace of silent realms. I have seen the shining light that is born of the wheat. Why am I bringing this to you? Because I claim there is a feeling in there which exists, which you can recognize, and it really exists. And the question is, why does that exist? And you can't explain that in terms of physics alone, because this is totally out of the domain of physics. But this does exist. It exists in the universe, if there's one universe. It exists in the multiverse, if there is a multiverse. Lewis Watling, I believe with all my heart and mind there's a spiritual dimension to all being that cannot be encapsulated in scripture or in creed. An essence that loses creative force when its communication depends on the use of words alone. It can, I think, be readily made manifest through metaphor and poem or story, yet I'm deeply aware that even when presented in such a form, the truth remains partial. For me, there's a reality that belies beyond our presently misdirected concern for the fruits of economic power. It's only when we acknowledge our deeper inner need to discover meaning in existence we begin to harvest the fruits of the Spirit. This is kind of evidence of existence. This exists. Now, it might be pure delusion in some sense, but you cannot deny that this kind of thing exists. So, in my view, there are intimations of transcendence in morality, ethics, aesthetics, beauty, companionship, love, creativity, science, creation, and existence and spiritual experience, a broad experiential evidence about the nature of the universe or any multiverse that includes us. You can argue that they are all illusion, or you can argue that they are real. You cannot deny that they actually exist and have to be explained, and they cannot be explained purely in physics terms. I've got to finish off now. Do the arguments against realized infinities in this talk argue against the concept of infinity in relation to the nature of God? Something from the theologians. I'm agnostic on this one, but tending to say yes. I think the concept of infinity is used far too casually, both in physics and in theology. I think the concept transcendent would do in theology, and the word infinity should be used lightly or carefully, if at all, in theology, just as in physics. You could ask, does the multiverse imply the idea of multiple gods? Is there a separate God for each of these universes, as people believed in the old days? Well, I argue against this. One God could have created a multiverse rather than a single universe. However, note that if one proposes the idea that everything can happen happens, One can reasonably argue that some universes will have a creator God and others not. How about that as an idea? Well, the issue is what is prior, the multi-universe mechanism or God who created it, from the viewpoint of those who believe in theism. Thinking about that could be an interesting and throwing light on the nature of creation. Is the idea of a multiverse useful? In a naturalistic context, yes, it does have explanatory power, no question about it, and that's why so many people are pushing it today. In a theistic context, it's not necessary. A small number of other universes is palatable, a great many is not. Such numbers are not needed for explanatory power in the context of a theistic explanation. It does raise the interesting issue. Does God need to learn as he or she creates the universe? Did he or she get it right first time? In that marvelous novel Star Maker by Olaf Stapledon has God trying time after time and getting it wrong and trying again and getting it a bit better. Maybe God had to go through a process of learning creating the universe, in which case there would be a multiverse as God tried different things as described by Olaf Stapledon and Star Maker. Is the degree of faith required to believe in a multiverse more or less than that required to believe in a creator God? I argue that both, because of the lack of conclusive evidence in both cases, as regards the multiverse and God, the degree of faith required to believe in either is the same. To believe in God, you have to have faith. To believe in multiverse, you have to have faith. Why? Because in neither case can you prove, in a scientific sense, that the relevant entity exists. Both can be argued on the basis of reasonable extrapolation from known data. Neither is in fact provable. Despite scientific experiences, belief in a multiverse is just as much an exercise in faith as belief in a creator God. And of course, as I've emphasized, they're not actually contradictory. Does a multiverse in fact exist? I have no idea. You can believe what you like. What do you find aesthetic? What gives you the greatest comfort? Does an infinite multiverse exist? Almost certainly no. I'm prepared to argue strongly against the infinite. As to does a multiverse exist? I don't know. I don't think anybody knows. Some people believe strongly, some don't. Martin Gardner puts it this way. There's not the slightest shred of reliable evidence there's any universe other than the one we are in. No multiverse theory has so provided a prediction that can be tested. As far as we can tell, universes are not even as plentiful as even two blackberries. But for defense of the idea, see Rees, Tegmark, Susskind, Vilenkin, Deutsch, and Lewis. And you will find strong defenses of the idea that will put the other viewpoint. So here's this guy. What he really was doing was looking out beyond the cosmic horizon and trying to see if there was a multiverse. That's what he was actually trying to do.
Well, thank you very much, George. A lot of food for thought there. I'm glad that you... some of you may know that the motto of the Royal Society is nullius in verba, which means, broadly speaking, take nobody's word for it. Go and find out for yourself. So I'm very glad that you emphasised that aspect of science. The floor is open now for any comments or questions from people. There's some microphones around, so if you just speak up, we'll pick them up. Does anybody want to start? Yes.
How do you think Occam's razor applies to your basic argument?
I think Occam's razor can be used to prove almost anything you want. Some people say a multiverse is an absolutely incredibly complex idea. Some say it's a very simple idea. Why? Because you can describe it in one word, multiverse. Well, you can say the same for God. Some would say it's an incredibly complicated idea. Others would say it's a simple idea because you can describe it with one word, God. I don't think Occam's razor gets you anywhere. I think some people would claim the multiverse is the simplest idea, some would say God's the simplest idea. And how do you talk about it? And one other point, of course, Occam's razor must be used with great care. Sometimes it gives the right answer, sometimes it doesn't. In most cases in biology, Occam's razor does not give the right answer. Biology is not simple.
Well, I know there's some biologists here that want to answer that. More comments? Questions? Yeah.
I think this is a misunderstanding of Occam's razor. Occam's razor doesn't say explanations have to be simple. It says explanations shouldn't have unnecessary parts. Now, if the multi-universe theory has explanatory power,
Which it does.
then it can't be the case that one can believe in it or not believe in it. How good is the explanatory power? That's a difficult, I won't understand your answer because I'm not a scientist, but that's what I would like to know. What is the explanatory power that would push one towards accepting it?
The explanatory power is very good. If you believe the multiverse actually exists, and I must emphasize not that there's a hypothetical one, but that it really exists, then out there are all these different universe domains in which the cosmological constant is large, it's small, the density is large, it's small, the expansion rate is large, it's small. Almost all of them will not be right for life, but somewhere, somehow, it's possible, probable, if you've got a complex enough multiverse that every here and there will be a tiny patch of the universe where things will be okay. It is good for explanatory power. It's a good philosophically based explanation.
Why can't it be just chance that the universe we have happens to be one that supports life?
It can be chance, and in the end, all of the scientific explanations are relying on this idea of chance. It's one of the big changes that has taken place. When I started cosmology, the assumption was that the universe was very, very special. It was assumed, something called the cosmological principle, that the universe is very special. The underlying philosophy of cosmology has changed into one that's saying everything is very random, everything takes place by chance, and that is the current underlying philosophy. Now, in fact, the multiverse is a way of trying to make a reality of the idea that everything takes place by chance. It's a way of instantiating it. However, I must emphasize that there is no proof that the universe is special or that the universe is general. That is a philosophical assumption. In the past, it was assumed by most people the universe was very special. Nowadays, scientists like to believe it's very general. But that's a philosophical assumption. You cannot prove it is correct or incorrect.
I just wonder if you could expand on whether scientific theories are a product of the society we live in, therefore, because if you've gone back a few hundred years, people would have said, you know, there's a theistic society, we know our place in the order of things, whereas modern, postmodernist views say, you believe your truth, I believe mine, you know, believe what you like. Do you think these so-called scientific theories are mirroring social views in that sense?
In terms of hard theoretical physics, I don't think they do. I don't think Newton's laws of motion in any way mirror the society in which he lives, or Newton's law of gravity. When you get to the social sciences, you're on totally different ground. Biology is kind of halfway between, but when you're talking the hard sciences, I don't think they do. But
multiverses aren't hard science.
But what is interesting is that most scientific ideas do not have only one representation. Most of them can be represented in many different ways. The idea of gravity can be talked about in terms of forces, or potentials, or variational principles, or curved space-times. There are different ways of doing it, and social convention can make you choose one of those representations as one you prefer over the other one.
I think perhaps you're disqualifying multiverse theory unfairly, as you're saying that it's unscientific on a very, very outdated philosophy of science. So you're using a view of the philosophy of science that's, say, like 50 years out of date.
Well, if you're proposing...
line between something that's scientific and unscientific.
Well,
and actually, multiverse theory is scientific, but it's just a very weak theory.
Well, I think that you're putting your finger on the core of the debate that should be taking place, because the core of what should be being debated is what is a genuine scientific theory or not. You're dangerously close to saying that it is not necessary to verify your theory. You can say it's true if you believe it hard enough, which is where we went wrong thousands of years ago. The whole course of the scientific endeavour came because we thought things should be testable. the multiverse proponents are stepping back from saying they're testable. They're stepping back to saying you don't need to test it. It's such a good explanatory hypothesis, we don't need to be able to test it observation. That's a very, very dangerous move.
All scientific theories just they exist on a spectrum of how untestable they are. There aren't some things that are observable, some things that are theory. It's just a spectrum. And you can't just, it's not just a crude division.
No, I agree one has to take it very seriously, and on my view, I think one should, from my viewpoint, I don't know what your viewpoint of the theory of the philosophy of science is, I would pursue the Lakatos view about scientific programs, progressive programs and so on, and I would say that would be the way to go. But I do not see any of the multiverse proponents seriously engaging with the philosophy of science. On the contrary, people like Stephen Weinberg are very derogatory about the philosophy of science. Now, I know there are reasons for that, but where they are going is territory where it is essential, in my view. If you're not going to step over the board into unacceptable territory, it's essential you do engage properly with the philosophy of science, and none of the books that I have shown you there engage properly with the philosophy of science.
You mentioned Deutsch a couple of times, just in passing, and he invokes this kind of quantum branching multiverse as an explanation for quantum computation. And so he at least proposes a causal link between these separate universes. But I guess I may have misunderstood this. That's not the kind of multiverse you were talking about.
I have avoided talking about that, and if you want to pursue it, I would hand over to John Poppy, who knows far more about this than I do. I have just found that whole idea, there's a huge problem with the foundation of quantum mechanics to do with measurement collapse of the wave function. This is a way to try to get around that. It doesn't, as far as I'm aware, make any testable prediction, the Deutsch's idea. And I've tried to ask simple questions. And when you ask simple questions, you're told you shouldn't ask them. I've tried to ask the people who talk about the branching. Well, please tell me, how often does it branch? Does it often every microsecond, every millisecond, every nanosecond? And they don't tell you how often it actually branches. It just is a very simple one. But in my view, I just can't make sense of that, so I haven't pursued that one particularly. I don't know how you make sense of it. And I would have to hand it over to some of the quantum physicists.
George, can I just say that quantum computation depends upon the superposition principle. It doesn't for a minute, in my view, depend upon the existence of these multiply realized.
That's right. That is exactly right. Quantum computation has been claimed by Deutsch to be a proof of multiverses, but it isn't a proof of superposition, but not multiverses. And to my mind, what is happening over and over again in the multiverse game is that the scientists who believe in it so strongly that they push the evidence a bit. I didn't quite emphasize that with Susskind. It was a bit late, so I didn't emphasize that. But Susskind emphasizes, according to him, the one testable thing about multiverses is that the universe must have open space sections. K is -1 in cosmological terms. What he doesn't tell you in the book where he makes that claim is at the time he made that claim, from all of the best data from the WMAP, plus all of the large-scale structure evidence at that time, when he wrote that book, the best evidence for the capital omega, the density of matter of the universe, was 1.02 plus or minus 0.02, which means if you take the data at its face value, it said the universe is positively curved, not negatively. In other words, it contradicted what I said. Now, certainly that data doesn't prove the universe is, there's huge uncertainties, and I would never say that that evidence proves the universe is positively or rather negatively curved. But it is an indication, as far as there is an indication from the best data at the time Deutsch wrote it, the evidence pointed marginally, ever so marginally, to positively curved, not negatively, which contradicted what he said about multiverse. He didn't explain that in his book. And this keeps on happening time and time again in the multiverse debate. People do not point out the things which are pointing against what they're saying.
That's human nature. Yes. Shall we take this as the last question, and then we'll move on soon.
My question relates not so much about the multiverse, then rather about our universe. But you were just mentioning the difficulties about using infinities in physics, and I was just wondering what were your position about the initial singularity. Do you think that it's kind of an unfortunate behavior of general relativity which will be solved in a more ultimate theory, or do you think that it really has a physical meaning as such?
Well, I think it's is zero as bad as infinity? I think that's the, like the initial beginning of the Big Bang. Yeah. Is zero as bad a concept as infinity is?
Oh yes, that's a very interesting point. Yes, zero and infinity are duals of each other. There's a wonderful book called The Biography of Dangerous Idea by Martin Sark, talking about zero. And so, yeah.
The idea was a little bit different. So it was just to know if actually the physical infinity, the initial singularity was only a mathematical concept, which is actually a result of GR, general relativity, or if it was more having really a physical meaning, which would be the meaning that GR gives, and which would make it solved in a more ultimate theory.
Yeah, so it's the initial idea of the singularity at the beginning of the universe. Is it, does it have physical meaning, or is it just a consequence of general relativity? Is
it just mathematical?
Is it just mathematical?
Well, it is a theory. Theory. What are you thinking about that?
Yeah.
If we had time, I would ask Stephen to give us an
I don't know.
The answer was he doesn't know. Talking about as we follow back from the present day into the past, we know the physics very well back to the time of last scattering. We know pretty well until the time of nuclear synthesis. As we go back to inflation, we don't know that well what is going on. When we're talking before inflation, we're starting to guess very widely. When we talk about the actual creation of the universe, we're talking about issues which aren't scientifically testable, and there's this huge extrapolation going on again, and we can guess, we can have wonderful guesses about it, but we cannot prove anything about it.
Well, I think that's a good note to end on. There's quite a lot of things we still don't know, even though there's many distinguished people here today. Well, let's thank Professor Ellis very much, and then just before we do so, I'll remind you again there's some free refreshments in the room at the back, and there's a bookstall there, and Rodney would just like to say something.
Yes, and let me give a notice. The discussion on this topic will go on. There's a whole day conference on it actually on the 24th of November in Downing College, being organised by Bernard Carr, whose book was described, I think, as balanced and fair. Yeah. During that talk. With more theological input too from people like John Polkinghorne and Keith Ward, and I'm speaking at that as well, and another cosmologist called Peter Coles. So do look out for that. It's organised by the Scientific and Medical Network. You can Google them and find out the details. Otherwise, Bernard here has some brochures. So thank you.
Thank you, Rodney, and let's thank Professor Ellis.